Hello, I'm Santiago Mol Lopez, and in this video about derivatives, we will be applying the chain rule to compute derivatives and also reviewing the derivatives of certain trigonometric functions. The requirements would simply be to know the derivatives of the elemental functions. Let's start by applying the chain rule to the derivatives of the trigonometric functions. For example, imagine that we have the function f of x, which is the sine of g of x. How is that differentiated? The derivative of the sine of g of x is the cosine of g of x. Notice that I differentiate the sine and I leave the g of x without differentiating and then multiply by the derivative of the function g of x. The derivative of the cosine function of g of x has the following form. You should remember that the derivative of the cosine function is minus sine. It would be minus sine that changes. The function g of x is left without differentiating. And then we multiply by the derivative of the function that is between parentheses. And what about the derivative of tangent? The tangent of g of x would be in the form of 1 plus the tangent squared of g of x, the g of x without differentiating, multiplied by g prime of x. The derivative of the tangent function may appear a bit unusual to you, but you must also remember that the tangent derivative has two expressions. One could be 1 over the cosine squared of, in this case, g of x, and the other would be 1 plus the tangent squared of that expression, of g of x. In this case, I use the second one, 1 plus the tangent squared of g of x multiplied by g prime of x. Let's examine examples of these three functions. I'll provide the formula here so that you can see the pattern of how they are applied. Let's see it using specific functions. What happens if someone asks us to calculate the sine of x squared plus 3x plus 8? In this case, we need to identify what is g of x in the formula. G of x is represented as x squared plus 3x plus 8. How do I then apply the formula of the chain rule? In this case, the derivative of the chain rule. Very easy. I substitute the sine with cosine because the derivative of sine is cosine. And I write the polynomial that I had there exactly the same. I do not differentiate it. Cosine of x squared plus 3x plus 8. And now, following this formula, I multiply by the derivative of g of x. Remember that g of x was this polynomial. Therefore, the derivative of the polynomial would be 2x plus 3. This derivative is very simple. The derivative of x squared is 2x. The derivative of 3x is 3. And the derivative of a constant like 8, in this case it would be ilo, the result, 2x plus 3. Let's see another example where we add some complexity to the situation. What happens if we have the sine of e to the power of x plus x cubed? Don't worry at this moment, as you won't need to graph or manipulate this function. Your only task is to calculate its derivative. Although it may appear unusual, there's no need to be concerned. Let's apply that formula. How would it be? We start with the sine function, following exactly the scheme. The sine function transforms into cosine, and I precisely replicate the expression within the parentheses. E raised to the power of x plus x cubed. Next, I multiply by the derivative of g, where g is what was inside the parentheses. It is e raised to the power of x plus x cubed. Although it seems complicated, it is not at all. The derivative of e raised to the power of x is e to the power of x, and the derivative of x cubed is 3x squared. Therefore, we enclose it within parentheses. These parentheses are crucial. We now have the derivative of sine for e raised to the power of x plus x cubed. Let's examine another example. The sine of the natural logarithm of x. How do we calculate this? We'll begin by determining the derivative of the natural logarithm of x, which is 1 over x. Now, what is the sine of the natural logarithm of x? Let's continue following the formula. The sine becomes cosine. The derivative of the sine is cosine. The natural logarithm remains unchanged. And then we multiply it by its derivative, which, as mentioned earlier, is 1 over x. Therefore, we arrive at the desired expression. Now, let's explore some examples involving cosine. What happens when we have the cosine of a function g of x? In this case, as you've seen previously, the formula would involve a negative sign, as the derivative of cosine is negative sign, applied to the function g of x without differentiation, and then multiplied by the derivative of the function g of x, which was between parentheses. Let's start with an easy example, the cosine of x cubed plus 3x squared. When we apply this formula, the cosine function transforms into minus sine. The function within the brackets remains unchanged, which is x cubed plus 3x squared, and then we multiply by the derivative of that function, which is 3x squared plus 6x. Another example, we have the cosine of 3e to the power of x divided by 3x squared. It is exactly the same. We apply the formula, and we have that the cosine is transformed into minus sign, and this function is left exactly the same here, times the derivative of this function. The derivative of e raised to the power of x is e raised to the power of x itself. Therefore, when we have 3 times e raised to the power of x, the derivative is simply 3e raised to the power of x. Additionally, the derivative of x is 1. We just follow the pattern outlined by this formula. Now, what is the cosine of 3 times the natural logarithm of x? As we have seen in the previous examples, the derivative of the natural logarithm is 1 over x. Therefore, what is the cosine of 3 times the square and the square of x? We apply the formula, minus the sine of 3 times the natural logarithm of x, as you can see here without differentiation, multiplied by the derivative of 3 times the natural logarithm of x, which is 3 over x. Finally, let's explore some examples using the formula for the tangent of g of x. I'll leave it written here so we can visualize the pattern. I remind you that it was 1 plus the tangent squared of g of x times g prime of x. In this example, we have the tangent of 5x to the fourth. Calculating its derivative is straightforward. The 4 comes down in front, and 5 multiplied by 4 is 20. Consequently, the result is 20x cubed because we subtract 1 from the exponent. Now, let's apply the formula. According to this formula, the derivative of the tangent of 5x to the fourth would be 1 plus the tangent to the square. Notice that this square comes from the formula. We have not put it for any exponent that is already here. The square of the tangent of the expression g of x without differentiation, which is 5x to the fourth, multiplied by the derivative of 5x to the fourth, which is 20x cubed. Be cautious here. It might be tempting to attempt to differentiate the entire expression, but you only need to differentiate 5x to the fourth, which results in 20x cubed. Let's examine another example, the tangent of the square root of x. While it's easy to deduce the derivative of the square root of x, it's much more efficient to have it memorized, especially for solving exercises quickly. I remind you that the derivative of the square root of x is 1 divided by 2 times the square root of x. Let's apply the formula that we have up here to the tangent of the square root of x. In this case, it would be 1 plus the tangent squared of the square root of x. Note that there isn't the product of the derivative of the square root of x. Next, we multiply by the derivative of the square root of x, which would be 1 divided by 2 times the square root of x. It may appear complex, but it's actually quite manageable. What is the tangent of the cosine of x? Here, we've combined 2 trigonometric functions, and we can simply apply the formula. We don't get confused just because there's a cosine inside the tangent. What is the derivative? If I apply the formula, it results in 1 plus the tangent squared of the cosine of x. And this is precisely the same function without differentiation. And now we multiply by the derivative of the cosine, which is minus sine of x. If more or less you have captured the essence of the schemes we have seen, you could derive any function, no matter what function they put us here. What have we seen in this video? We have seen how to calculate the derivatives of the composed trigonometric functions. I hope this helps you. Thank you very much for your attention.